Sascha is one of the main contributors of SuriCata. He's doing actual development. He's maintaining the Debian package in Debian, for example, and has been speaking and attending SuriCon many times. Go ahead.
I'm sorry.
I'll try this way. We've seen Matthias as well many times, I think. You've been speaking at least once. We've been meeting more than once. I don't recall exactly. You're working with a very exciting open source project called VAST that I know that many people in the community are exploring for processing SuriCata events. Benno, I haven't met before, I think, but let's give a warm welcome for these three amazing people that will talk about working with SuriCata output in their great tooling. So please a warm welcome for Sascha and Matthias.
Thanks, Victor, for the introduction. Thanks for the opportunity to speak here. It's been a great conference so far. The past 2 days have been absolutely amazing. Really looking forward to the rest of the talks. Any technical difficulties?
Just the HDMI. So you think 4K?
Yeah, I think the image 4K doesn't work. At least we've had problems with resolutions before, so I don't know.
Turn the resolution down.
Maybe.
Stay tuned.
Okay.
Conferences are these great moments where you can ask questions like, how many engineers does it take? You would think that these are solved problems by now. You should be able to see it here if it works.
I bet it's not.
Okay.
Right?
I think we can get it. Okay, we'll scale it down.
Yes.
Ah, there you go.
Okay.
There's a clear pattern, right? Okay, so this is our talk. This is our talk on compaction and how to keep SuriCata data useful for longer. Before we start, just a couple of quick words about ourselves. Hi, I'm Sascha. My background's in bioinformatics and in sequence processing and annotation handling, but for more than 6 years now, I've been working at DCSO, German managed security service provider, working mainly on DPI and metadata processing. And I'm very happy that that job has given me an opportunity to be involved in other open source and free software communities such as SuriCata and Debian, as Victor already said.
Yeah. Hi, I'm Benno. I'm a C++ developer at Tensier, and before that I was working at Apache Mesos, the focus on distributed systems and high-performance programming.
Yeah, hi, I'm Matthias. I'm here now for the third time. I'm very excited to speak to all of you. I spent a decade prior to showing up back in Europe and getting more involved with the SuriCata community. I spent with the Zeek team. In fact, I was Vern Paxson's first PhD student, so I was spoon-fed with Zeek for over a decade. And by now, since we're working with our software downstream of all of the high-volume network telemetry, and we have embraced everybody, including the SuriCata community, and we are really, really excited to show you what we have today. There's going to be lots of meerkats, and yeah, even if you're not interested in the technical stuff, I think the meerkats we put a lot of effort in.
All right, so let's just get started by stating the obvious. I think most people in the room will know SuriCata isn't just an IDS whose main goal it is to produce alerts, so telling people about anomalies in the traffic that it sees. It's also a network security monitoring tool. So that means it tells you things about everything, every little thing that happens in the network, creating data points for each of the protocol transactions that it sees. The question is, why do we want to have this data? What does it give us? So it allows us, first of all, to do other forms of detection. So, for example, instead of just evaluating rules and generating alerts, it allows us to do retro matching. So match new indicators on historical data and act as if we had known about a specific thing before. And also it allows us to do detection that needs a bigger picture of things that happened. So it needs to do some data mining on a bigger databases than just the traffic it sees at the very moment. And in addition, the metadata, once stored, allows us to do things like passive network enumeration, so trying to map out an organization's network, assign roles to hosts, to network ranges, and so on. That would give an analyst more insight into the assets it sees in that network. So while it might be tempting to just gather up all that data and store it somewhere centrally in a centralized location, there might be good reasons to keep the data close to the sensor itself. First of all, there might be sensors that, while they're inspecting a high bandwidth network, only have a low bandwidth connection somewhere to an HQ. So that means you can't send everything home. And on the other hand, there might also be some requirements that would require your data to be close to the sensor, right? So the customer, whose data center the sensor might reside in, might not want to have this data leave its premises. So all these are different reasons why you might want to keep the data close to the sensor and not just send it off immediately. And you can see the problems that might come with that. So this is a cumulative graph showing the total ETH-JSON throughput of a sensor that sees about 6 gigabits of traffic with all the metadata, the protocol parsers turned on at maximum detail. And you can see that for a week of metadata, we are at about 20 terabytes of data of raw JSON that need to be stored somewhere. And you can see that it's pretty linear, so that situation doesn't change too quickly over time. So what can we do to counter that problem of growing data in a potentially limited situation? Well, you could just add space, right? You could just add new disks. You could just buy extra space in a cloud environment. But as I said, and that's the situation with most of our sensors, if there's just a bare metal appliance, just a regular hardware sensor sitting in the data center somewhere, and the customer doesn't have any more rack space to spare, then that's it, right? You can't just add new disks as you want. You could just compress the data. And I mean, while the overhead for compression and decompression is largely countered by efficient compression implementation these days, there's just so much you can do with compression, right? You can't go beyond a certain improvement there. You could just also move the data, right? You could move it to a slower but higher volume way of storing them. But then again, you run into the problem of potentially running out of rack space. You can just have a tape library stored right next to it if there's no more rack space. Also, data wouldn't be as easily searchable, right? If you don't have an efficient index to pull out the data the way the search queries want them, it's not as useful as it could be. And then the obvious solution would be just to delete data, delete old data that you don't want anymore. But the problem is, what do you want to delete? You might still need the piece of data you just deleted because you didn't know you would need it again, right? So can we do better than this? This is all the naive solutions. I mean, and then there's one thing left. We could just try to change the data, right? So you could try to have the format of the data that we store be guided by the questions that we want to ask on the data, right? So we don't want to delete events in the regular case. That would only be just a last resort. But before that, we would always want to try to make the data more coarse-grained. So just to show an example here, if we are faced with questions like, who looked up a certain domain in a particular time frame? If that's one of your usual questions, then you don't really need to store each and every single DNS lookup. It would be completely enough to answer that question by just aggregating them into one data point and then keeping the first and last seen timestamps and the count of them, as long as the source and destination IPs, destination port, and the contents of the DNS transactions are the same. So that is an example of transforming data to be able to answer the same questions with less data to store. So just to give you a quick recap of what different transformations we can use to arrive at that goal, we have a projection where we can delete entire fields but keeping all the data points, right? So every row here can be considered to be like an ETH-JSON data point, an ETH-JSON object, and all the columns here can be considered fields. So we can just drop fields. We keep the data points, but we take away some level of detail. We could do selection by removing entire data points, entire objects, which is what we try to avoid if possible. We can transform data by changing the contents of specific fields or by just adding additional data, additional fields if it's necessary. And we can aggregate data. So we can take rows or objects with similar data in them and then migrate them to only be one data point afterwards. And we are going to show how to apply these operations on data that are stored in a database that we're using as an example here. So let's just summarize the contributions we're going to talk about today. We're talking about compaction, which is providing a framework to operationalize these operations and trigger them in pipelines whenever we, for example, reach a time constraint or when we reach a space constraint. And we're also going to show how that was implemented in a database that is maintained by these guys from Tensor. It's called VAST. And at the end, we're showing you how we use that in production and going to show some data. So I'm passing on to Matthias for more details about VAST.
Yeah, so I don't want to dwell too much on it, but we need to know certain things because this is the vehicle for a lot of the analysis that we're doing with EVE data. So why does VAST exist? So we set out to build VAST because we struggled with bringing two things together. On the one hand, the data in a SIM is typically locked up in a proprietary format, and we cannot bring the analytics that we want there in order to do these transformations unless the SIM provides it already. And on top of that, we saw Marcus talk yesterday. There's so much analytics you just want to bring to the data, and that builds on an open data infrastructure. That's really not the world we have right now. Everybody has a custom binary format on disk, and then you have to go through a narrow API. And so that makes it really difficult to bring analytics workloads to security data. And on the other hand, we could always use a ClickHouse, a Spark, or something, but these things require a lot of data engineering to bring them to the security domain. And security people are not data engineers. And so that's what we wanted to solve. We wanted to really make it easy to bring analytical workloads to the security domain and provide an open platform. And open data interoperability is something that we are all passionate about at Tensor. We're passionate about open source, open interoperability with the security data first mindset. And for example, open storage means that you own the data. It's written in a standardized format, Apache Parquet. And with VAST, what we're trying to do is really decouple high volume telemetry acquisition on the one hand from the downstream analytics. That's always coupled today. And that makes it very difficult to do detection engineering, threat hunting, and in a sustainable fashion, if you want to, without changing the lower level layers, the data layers. And so we built VAST with these principles as a high performance telemetry database. Initially, we thought it was just high volume telemetry acquisition. That's what came out of basically the time at Zeek. And then we embedded Apache Arrow as the cornerstone technology that made it really easy to use a lot of the data science ecosystem out there. Basically writing data, EVE-JSON data in Apache Parquet that you can use your AWS Athena, your ClickHouse, your DuckDB, whatever supports Parquet you can now use, and you've basically opened it up for a variety of analysis. So that is, I think, the main thing to take away. We talked in 2019 how we pivot from alerts to PCAPs through the community ID. We had a talk about automated retrospective detection. That was also with DCSO last year. And yeah, we have also something planned for 2023, and stay tuned. So basically, to understand how does it work roughly, data flow is EVE-JSON is the input, parsing that, demultiplexing that into different schemas, if you will, per flow. These are our data frames internally, and they get written then in an open format like Apache Parquet or Feather to disk. That's the bare bones ingestion architecture. And that scales nicely on a laptop, a couple of 100,000 events per second. If that's just alone your use case, just making the data easy to use, that already would be doable today. DCSO runs VAST in production for around 2 years on their sensor fleet, and this is roughly how the architecture looks like. There's a security content management in the top left that drives a lot of the detections. That's central. That one are rules. Basically, it's also the threat intelligence engine. That's the tip as a service and curating threat intelligence that gets packaged up. That was our last talk last year about how kind of that gets operationalized and then deployed to the SuriCata sensor. SuriCata runs on the appliance, ships the logs on the one hand to VAST, and the alerts specifically, that's kind of a very small percentage of the overall data back to the headquarters. And then the analysts kind of do federated queries on top of that. To give you roughly an idea, there's a one-to-one mapping of a Eve JSON log to a VAST schema, and the types are a bit richer than JSON, and that comes back later. That allows you to do really cool stuff like top K prefix searching on a /27 or so instead of trying to wrangle with strings all the time. Currently, these have to be handwritten, but soon, we'll try to add some inference so that you don't even have to write these schemas anymore. That makes it a lot easier than to use out of the box. Today, we're talking about compaction, and whoever runs VAST and SuriCata or just SuriCata on a confined spatial environment, you will always end up running out of disk space. So we try to break this down because there's multiple levels in terms of sophistication about compaction. And the first thing that you can imagine is just deleting data off. When you hit a certain quota, 80 to 90% disk space, less than X, you can just delete the old data. But if you do that randomly, then you may delete the data that's more important than other things. So then you can maybe go to the next level and try to get a little bit smarter. And if you just delete the oldest data first, then with the assumption that there's a decay function, older data is less relevant than new data, then that's a mental model that makes it a little bit more sophisticated. But not every data is equal. Alerts, flows, SMBs, you may associate something with them. You may associate a different relevance to them. And I think let's consider this concept of H a bit more. Here we have flows, for example, the green boxes. The blue ones were DNS, for example, and the red ones are alerts. So what we have here is if we kind of see these as blocks of data, and if we try to enumerate them in a total order in terms of age, then what we would get is one alert is younger than this block of flow data is younger than the block of the DNS data, etc. So we can basically, at some point, we may just delete from the oldest to the newest data type, and then we kind of go from left to right through this path and until we're back into our desired quota. So if we try to linearize, that word, that sort of view, then we can arrange them Tetris-like in a sequential fashion. So we would delete the small red guy first, then the green guy, then the blue, and so forth until we are back in the capacity that we have, the quota that we've given. And that's the question is like that's not enough. Why do we want to the alerts? Why do we delete them first in this naive model? Like maybe we can really include the event type as a first class element in the compaction algorithm. And I'd be curious, Benno, maybe what we can add here is the event type as a traffic mix. Does that work?
Yeah. So in fact, level 2 was what we actually had implemented in VAST when we started this project with DCSO. And one of our first ideas was to have the static traffic mix distribution. But when we looked at actual real-world data, it turns out that this is wildly different across different hosts. For example, if you look at these two, the upper one sees a lot of DNS data, whereas the one right below sees almost no DNS data at all, and it's just all flows and I think what's the other one? HTTP maybe. And if we would have a static distribution here, then we would waste, of course, a lot of space. And on the other hand, if we want to do this optimal, we would have to go around for every host, measure what actual traffic do we have, what makes sense for this particular host, and that would be a nightmare to maintain. And yeah, that doesn't scale. So we need something a little bit more flexible. And then our next approach is something that we call virtual H now. And the motivation here is that essentially we want to give relative importance to different event types. For example, we want to be able to say my alerts are more important than my DNS events, or my metadata events are more important to me than my flow events. But we don't want to have this, this fixed static distribution, because that only works if you know the incoming traffic mix, and that is static over time as well. So what we do is we attach a weight to every type, and then we look at the age of every partition. So these partitions, by the way, they are partitioned in time. So every partition covers the time range from some begin to some end time. And we divide the age by the weight. And we divide so that higher numbers mean more important data. And by doing that, for example, the green the flow data has a weight of 0.5 in this example. And the blue data has a weight of 1. And the alert data has a weight of 2. And by doing that, we get a virtual age order. And it's interesting to note that this actually is not a fixed order, but it depends on the current time. So if you look at right now, you have the traffic is exactly the same as it's coming into the sensor. And the further back you go in time, the more important the effect of the weight becomes. And then we can go and use the same algorithm again, go to the oldest virtual partition and just erase that. And if you're lucky with your event types, that's already nice. Because if you're lucky, then your important data, the alerts in this case, they are small, and they can be given a low weight, and the bulky data is not as important and can be erased first. But in the real world, of course, we are not always that lucky. For example, at DCSO, alerts are almost the least important data because they're stored in a separate database. So we need something a little bit more flexible. And that is the next part that was also covered in the beginning, that we want to not just erase data, but we want to transform it. And the idea here is that by transforming data, hopefully we can write these transformations specifically per type, so we can apply not just a generic compression, but a lossy specific compression algorithm that results in the data being transformed into a new type. And that type then again can be weighted higher again because it has more relevant data now. And to get back to the previous picture, that of course means that we can also store more data within our given capacity. And that is actually what we did implement for VAST. And in VAST, like this whole thing is called compaction, and in VAST, how to do that is we define so-called pipelines. Each pipeline is a set of operators that are applied to a given data set in a specific sequence. And in reality, these are actually end-to-end mappings, so they can have an arbitrary number of inputs and outputs, but for this talk, we always only consider one-to-one mappings. And these are actually plugins. So you can write your own C++ code to define your own pipeline operators, but there are also a number of predefined operators that come out of the box with VAST that cover most use cases, I would say. And in particular, the one that we are going to use for now is the summarize operator, which essentially just does that. It aggregates a set of input data. And these pipelines can be triggered either like we have we provide multiple triggers for these pipelines. Either they can be triggered by exceeding a threshold amount of disk space usage, or they can also be triggered after a certain age of the data, which can be useful, for example, for compliance reasons. So you can say something like, I don't know, my personal user data is not allowed to be stored more than 7 days. So after 7 days, I trigger a pipeline that erases that field from the data. And yeah, in the disk space case, it's important to not go to 100%, of course, because all this happens while the system is still running. So we need to have some leftover buffer to still store the new incoming data while we do the compaction. And yeah, with that, I hand back to Sascha.
Okay, so let's quickly talk about how this would look like in practice. So let's get down to the configuration files that we, for example, at TCSO use to actually bring this into practice. So what you're looking at is a part of the VAST configuration file, in particular the section that deals with compaction. So as we have heard already, compaction is implemented as a plugin in VAST, so this is where the configuration lives. And for example, this is a configuration that implements this sophistication level 2, just simple rotation, right? So we can see that we have space-based compaction where the disk budget that's currently used according to a given binary, so that binary gets executed and gives you a numeric value, and it's checked whether this value fits into the disk budget, high and low value, and that's checked each hour. And if that's the case, we're going to remove old data. And there's also a time-based constraint here where each hour we check if, for example, a given set of types, so for example, Suricata DNS data, alerts, and so on, are older than 90 days, and if so, they are deleted. So this is the simplest case. It doesn't incorporate any of this aggregation stuff that we've been told about. This is just simple rotation, right? This is as basic as it gets with this functionality. To look at something slightly more involved, we're looking at level 5 now, including compaction with aggregation. And again, we're looking at a space-based compaction configuration, but this time we have an additional section that specifies weights. So for each type that VAST knows about that deals with Suricata if JSON, so for example, we're looking at flow, DNS, SNMP, SMB, HTTP, and TLS. For each of those, we have defined a processing pipeline that does the aggregation. I'll look at an example of that later on. And assigns a weight. In this case, we use uniform weights, but it's absolutely possible to, as we already presented, it's possible to pick different weights depending on the relative importance or the perceived importance of the data that we want to store and aggregate. And then, in addition to the native Suricata types, we also need to define new types for the aggregates, and these are given a higher weight to signify that we want to keep these around for longer because they're going to be our more permanent storage. And this already implies a little bit that there might be more than one level of compaction, but we'll return to that point later on. All right, so we've referenced a pipeline here, outlined in red. And this is an example for flow aggregation, which I'm going to show in detail. So each pipeline that's referenced in the configuration also needs to be defined separately in order to specify the exact operations to be performed in that pipeline. And in this case, we're using 3 different operators. One of them is summarize, which does the actual aggregation, and then 2 other operators to transform a regular Suricata type into this new aggregated type. So let's take a look at the summarize operator first. The first set of configuration items that we can specify is a set of fields that serves as the criterion for aggregation, right? So whenever a set or a tuple containing the contents of these fields is identical, the corresponding if JSON objects are candidates for aggregation. This is basically like a group by statement in SQL. So for flows, for example, we would like to aggregate those flows that have the same source IP and destination IP, the same destination port. We can't obviously expect that the source port be always the same, and the protocol, which is TCP or UDP. And we want to do this with a resolution of 1 minute. So we want to aggregate the flows that fit this description over intervals of 1 minute. And the aggregate section then defines what fields we want to keep in the resulting new data point and how to arrive at the new data points looking at the incoming set of data points. So for example, we're going to introduce a new timestamp min and timestamp max field, which uses the min and max aggregation functions on the original timestamp. We will also sum up all the packet counts to the server. You could also do that for the one to the client. We're taking the minimum of the flow start, the maximum of the flow end, and we are setting the alerted Boolean field whenever any of the fields in the input flows is set. And there's also additional aggregation functions that allow us to collect values. So for example, if we decide that we still want to keep the source ports, but we just want to enumerate them all within the aggregated data point, then this is possible using the distinct aggregation function. It basically just collects unique values accounted in a particular field. And then again, we add a new count field that just simply counts the number of individual values in one particular field. For example, if we look at the count of event types that we see, then we would get the count of the aggregated values. And what we just do at the end, which is the right side of this configuration, we simply change the event type from flow to flow ag and move it to a new schema within VAST itself. So that's an example for one pipeline, and there's, of course, equivalents to this for all the other if JSON types tailored towards the fields that are in there. So how would this look like if we apply this to a flow? This is an example flow if JSON object. So looking at the group by fields, we can see that we have source and destination IPs, destination ports, protocol, and timestamp. And let's just assume that we have 14 of those, which with identical values for these fields. How would an aggregated version look like? So first of all, we can see that the resulting data point, which is on the right-hand side here, has moved from event type flow to event type flow ag, and has a count value of 14. And the min and max timestamps refer to the minimum maximum of the individual timestamps in the incoming objects. Source ports are gathered in a list in here, and packet counts and byte counts are just summarized. And this way, I think it's kind of obvious that we will have a lot of space reduction by just folding all these individual flows into one by keeping as much of the information that might be important, for example, for network enumeration and so on, in the database and not deleting it.
You can still save a bit more space by removing the community ID empty array.
True. So the comment was that by removing empty fields from the JSON that don't add any value, would save even more space. I think that might be a different question for Tenzio, whether that's actually stored on the database if there's no content in there. But yeah, you're definitely right.
Just the real-world effect is actually marginal because the data is internally and both in memory and on disks stored as a columnar representation. And if you have a column of, and the batch size is 64K by default. So if you have a 64K column with all the exact same empty value, it's exactly stored once, both in the Parquet file and the in-memory representation. So that is, it's like the argument JSON compresses really well because it's so elaborate. It's the same argument here. Like this columnar representation makes distributions of that type compact effective.
All right. So much about looking at one example in detail. I think we're going to be moving on to an example application on a data set, and I think that Benno is going to elaborate on that a little bit.
Yeah, so Sascha nicely prepared a SuriCata version of this realistic cyber defense dataset from CSE 2018, which apparently had a source data of 150 gigabytes of PCAPs. And yeah, we just ran our compaction pipelines against this data. And this graph is showing that the reduction in space that we achieved. I think the y-axis is wrongly labeled, actually. So what you see is the percentage of the file size after a compaction application. So like before we compacted, all partitions at 100% size, and then the height of the bar shows the new size. So in this example, SNMP data was compacted the strongest, down to only 24% of the original size. and TLS data, for example, compressed the worst. We did this for 2 different resolutions. So if you remember, we combining packets with the same source IP, destination IP, and destination port and protocol across, for example, 1 hour and 1 minute. And as we expect, the coarser we do the aggregation, the more we can reduce space. However, the effect is actually not as strong as you might intuitively expect. In particular, if you look at SNMP data, there's almost no effect. And if you look at the source data, actually only about 2% of the SNMP packets get aggregated at all. Most of them are actually unique. So where the rest of the space savings comes from is from how the summarize plugin works, so that the fields that we don't summarize, they actually get dropped from the input data. And this makes a huge difference. For example, in this example, we are able to drop the vars field and the PDU type. And this makes a huge difference, even more than like you see on the screen, because of course internally we don't store the JSON data, but we store it in a more efficient format. And strings are like the least efficient format to store. Like if you have an IP address or a number, of course, this would make a much smaller difference than if you can get rid of string data. And also by default, vars creates per column additional indexes and Bloom filters and so on and so forth. And of course, every time we drop a column, we have this knock-on effect that we also don't need to save the corresponding indices. And the nice thing about having this completely configurable is that like now you could go and like adjust in both directions if you want. If you say you want my aggregation, you can make the selection criteria coarser. For example, maybe you want to aggregate over multiple source IPs or over multiple dest IPs. Or on the other end, if you say that your PDU type, for example, is actually very important to the queries that you want to run, then you could just not get rid of it. And all of that is just a change in the YAML configuration. And also, as we announced, we have been running this actually in production at DCSO. And we also have a measurement from that. Of course, since this is a real-world measurement, it's really messy. In particular, please ignore this huge spike in the middle. That's due to something called automatic rebuilding, which we didn't cover at all, but it did mess up our data a bit. But like in principle, like if you squint a bit, you can roughly see what you would expect. Like the graph shows for every day, it shows the age of the oldest HTTP event on that day. And you can see the disk is filling up, filling up, filling up. And then at some point on the right, the compaction kicks in and the HTTP data, the age of the oldest HTTP data goes down because that gets deleted. But the aggregated HTTP data, which is shown in blue, is still visible. And the age of that goes further and further up. And if we had like clean data, this would actually be the red line would actually be a horizontal line and not increasing on the left-hand side. And looking at this for all the other data types, yeah, it gets even more messier because we have also more artifacts in the data. But like roughly you can see the same thing happens for all of our data. Like the non-compacted data gets deleted, the compacted data stays, and you can see further back in time. Due to this, with the same amount of disk space. And with that, I give for a few final words to Matthias.
Yeah, so we've seen the various levels 1 to 5 right now, and it's kind of obvious by design because we are creating new data types. Flow becomes then flow ag. We can do this in a multi-level fashion. So we could even consider flow ag 1 and then apply another pipeline on that, and that becomes flow ag 2 and so forth, so that we really get that long tail of the decay function to be arbitrary almost, up to get in those retention spans that we really need to detect things like solar winds out there beyond 9 months, 12 months. You know, some people are building data lakes with 18, 20 month where only compliance is the limit. And so if you can apply that principle of compacting recursively, then you're in the kind of end game. And you can really truly build something that matches exactly your needs in terms of retention span. And if you're not now have millions of dollars where you can just throw everything in AWS and don't have to worry about the cost, and even then, the costs are real. So if you want to bring down costs, compaction is as a mechanism that can be applied recursively is as sort of so handy, that composability aspect. So thank you. We are building VAST as BSD license open source model, and if you want to talk about open source, come talk to us afterwards. Kelly, I think I don't have to add anything after Kelly's talk, the importance of open source. We are a Hamburg-based startup, 15 people, and trying to build that for the security community, because we are incredibly passionate about enabling security analysts with data-driven tooling. And so join our community, check out our project. If you want something, come talk to us. We're here for you. And yes, we'll get to the point where the meerkats will always win.
Questions?
Hey, that was a nice talk. So we have been solving a similar problem in our company. So I saw that you have configured the weight. So is that a static parameter that you configure, or is that something computable that you compute with a virtual age or timestamp? How do you, get that weight value?
The weight is something that you currently have to specify statically in the configuration file. But that's your mental model of what data is more important than others. You have to kind of come up with your own way of importance and saying, my alerts are 5 times more important than my flows. But then basically what we saw earlier, that's a different approach than just taking a traffic mix distribution and saying 50% flow, 30% DNS, and some other distribution. And if the naive way would be say, I'm just going to try to keep that event distribution that I have. And then whenever I have, that kind of makes a static assumption about the event distribution. And that, since we've seen that changes across sensor and it widely changes, I think using this relative importance approach in terms of weights, that's not anchoring you, that one makes that's your input. And I think you could argue that you want to even derive or compute those weights dynamically, but I think most of the time that we don't have a real-world use case for that. But if you can come up with one where, say, find those automatically, it would be very easy to make that also like an automagic option in there or something.
Okay, so I have another question. After you compact the data, so do you perform some purging on the compacted data as well based on the storage or maybe the timestamp, age, or what is the criteria for that?
By purging the compacted data,
yeah.
Do you...
Maybe the log rotations or anything?
So the old data, there's basically the way to think about it. The old data goes into a T, and then it goes first in a pipeline that aggregates it, and that yields the aggregated data. That gets stored then. And then, if you don't have anything on the other side of the T, it just gets deleted. I think that's the example. Here, or actually a better example is, if you don't have a pipeline at all, stuff gets deleted. If you add a pipeline, it gets transformed, crunched together, and then fed back into the import path.
Okay.
And in this case, for example, the fact that the aggregated data have weight 1.5 and the other have weight 1 would lead to non-aggregated data being first compacted and deleted before the aggregated data gets deleted. They will only get deleted if there's absolutely no more space and you need to get rid of them. So that's another consequence of having these weights.
And so actually, if you look closely here, this is why the arrow is pointing not just up, but to the right, because the new aggregated data has a different weight than the 0.5. The 0.5 is the virtual space age. That's one already stretched. But if you have a difference of 0.5 to the new aggregated data, so it's younger, so to say, in the virtual space.
Can I have the access to the source code? I'd really like to check out or make contributions to the project.
So VAST is BSD 3-style licensed. We have a open core approach to keep it sustainable, meaning we try have a small set of plugins that are closed source in order to avoid getting AWS. And there's a few plugins that you can check out. Compaction is actually one of them that we don't have released yet, but the rest of the entire, like 95% of the vast code base is open source. And if you want to play, though, with it, we're also soon releasing a community edition. The name may be different, but basically where you have everything, you can play with everything, and kind of something between the open source and the commercial. So that is just, talking a little bit. Come to us with the later details.
Sure.
Kind of stretching.
Thank you.
A question from Andreas Herz from the Discord, and I kind of wanted to read it out. So he asked, question for the end. I know for some reason that in the past another level 0 is used to have more space by using butterfuzz. With Z-stood file system compression, this achieved often to compress the vast database down to 25% of its original size. Is there still the same benefit after compaction?
So let me try to rephrase the question. You're saying basically by using file system compression, you already get implicit levels, something like level 0 in here. That's not mentioned. And the data points.
Also historically, so for some context, Andreas Herz, who's still on that big screen there to the side, asked this question, and he's worked with Sascha previously at DCSO, so he knows VAST really well. And I mean, they've done this previously before we had compaction. So his question kind of was like, how do the two things like relate to one another? How well does the compression still work after you already compacted your data?
So I think with one of the few vast releases we added actually is transparent Z-standard compression in there, and that makes the effect of a general purpose compressor that is built into the file system like butterfuzz less obvious, so because then the entropy is already pretty high, and the additional file system compression cannot do that much. But it could be interesting research project to turn off the Z-standard compression in VAST and then see if you get better compression with file system level, block level compression like that you have in butterfuzz or ZFS. But right now we actually get really good results with Z-standard.
I would also maybe add to that the file system compression is necessarily a lossless compression, but what we do here is mostly lossy compression, so we do get better compression rates.
And one more addition directly to Andreas' question, because he mainly engineered the underlying file system configuration for the machines that we tested this on. So one of the measurements, the last one that included the retention time, that was made on a machine that already had file system-based compression active. So you can see that there's still a benefit or an improvement even though the machine already uses compression.
So thank you, nice talk indeed. Is there some level 0 missing that Suricata should be less verbose because there are different types of events and some can be quite big? I guess that's, you see that with the size of your boxes, and so maybe we should be less verbose in the first place somehow? What do you think?
It's really hard because then you're basically trying to make a judgment on this data is important for user X and this data is important for user Y. That's usually over time and the SMB analyzer, like it grows in terms of fields and it gets richer and richer and richer because we have more data, and I think it's going to be quite rare. But maybe if you want to have a Suricata mode that says kind of be like minimal or something, you could build in some of the projections. That could be something.
As a user X, I have my JSON schema that all of Suricata what can do, and I just remove all the lines that I am not interested in as user X. And there are many lines, or if it's just 1% and not meaningful.
So if you ask me, please don't dumb down Suricata output. Please include more detail. I can see that there's already some configuration options. For example, in HTTP, there's an extended mode that logs more information than the non-extended mode. So I think it should be up to the user to drop information they're not interested in, and just for everyone else, they should be able to get whatever they want. So yeah, that's maybe just my personal opinion, but it's obviously driven by what we're doing with the data. So more data is better.
And something, at least, maybe it's not the job of Suricata to kind of make that decision, or it's probably, if you think of Unix pipes, like if the output of Suricata is the firehose of Eve JSON, then why don't you just put a tool right after that, can make that decision for you? Yeah.
Thank you.
Is there more that SuriCata could do to help your weight assignment? Is there some things that SuriCata could help you provide to make that process easier and dynamic, as was discussed before?
From the help of, if you could argue that you add a new field in every Eve log that basically provides an importance metric that can be then used downstream for storage or simple ops management of the data set. This one is not important, but that's highly dangerous, I guess, to do, although you have much more context to make this decision. But take, for example, alert severity. If that is kind of an implicit field that tells me how important something is, and having something like that as an orthogonal mechanism for all logs could be something relevance, severity, that could be an interesting thing.
One might also say that the weights are a measure of your subjective feeling of importance, and that might be different for everyone else, right? It's a relation between types. So maybe it's not a good idea to predefine that or to provide that at the source, but rather have everyone who uses the data reason about what they consider more important than above other types for themselves.
Right. I guess I'm thinking about also things like if an alert has a certain severity, all the related event, like with the same flow ID, would automatically get a higher weight, or something like if you see certain data, like a new user agent that never been seen before, automatically assign more weight to that because you may want to hold on to it a bit longer. And just kind of thinking out loud now, but so what might be interesting to keep in your storage longer than other things?
I think this is interesting if you start to basically tell a story from a set of events, and maybe it's rooted in an alert, and then you have HTTP, SMB, like an entire sequence. And I think with the flow level identifier, we can, at least within a flow, we can correlate that, but being able to kind of propagate that taint, so to say, through other events that are related, that is definitely something that would probably, finding an identifier that makes it like a cross-event story feasible would be really interesting, because then you can just pin all the respective events downstream. It's like right now, for example, that's exactly what we use with community ID pivoting. We showed that in 2019. You can just give an alert, take the community, okay, pin all the flows for that one. That's kind of, it's a very making that more general for all event types. That would be, I think, highly useful. And right now there's no mechanism within Suricata to do that, or setting like things like setting flow bits, but then they get picked up later across event with different analyzers. Something that could be a mechanism for propagating the taint.
That raises the question of complexity versus clarity. That raises the question of complexity versus clarity of model, right? Because doing something like that would exceed weight definitions on types. That would also, we need to be able to look into the alert and then derive something that might, transcend the type. So not sure if that would make things more complicated. So it's always expressivity versus simplicity.
But I think you're touching on a highly important topic for everyone here is like, how do you create a story across events when you're basically escaping the fixed community ID? Like that's usually a sequence of events. We all do it in a hand-rolled fashion, but looking at a minute before, looking at a minute after, like those relationships are currently inferred downstream. in your processing engine there. And so coming up with more first-class primitives for linkage of events, even if it's not 100% there, like even you say, hey, these candidate things, I could basically, then you can, at least you get an option, a graph that you can evaluate that much, much smaller than trying to do fuzzy things downstream.
So the flow record actually has a start timestamp and an end timestamp, and the flow record should be the last record that you get. So that should define the range of, at least per flow, your search for finding related records, I suppose. But if you go cross-flow, it becomes much more complicated.
I mean, also, I think this works for the standard approach where you imagine something happens close to a certain event. But sometimes there's, things go dormant, bloop, a little bit later down the line where the temporal context is no longer there. And then maybe you just have a spatial identifier, like a Copal Strike session ID or something, that comes back later. It's time alone is always, I think, is one side of the coin. You need space too. And so that's where I think Suricata could help a lot, and at least trying to guess, if it's just guesses, like, hey, we think this relates to something, but then if you link across things, you have to keep state. And then you're back to square one, like, that's what we're trying to avoid, to stay in line and not drop packets. Hard problem.